Welcome to this review presentation of Chem 151 material for Chem 152. This is part 1 of the lecture set. In this lecture, we'll be going through the first 4 major topics of 151 review: net ionic equation, oxidation reduction, electron configuration, and balancing equations. And then in the second part, we'll be going through molar mass determination, dilution and molarity, and ideal gas law. If you look down at the description on the YouTube video, you'll find that I've got these broken up into little sections that correspond to each of these 7, so that you can go back and pull each one up as a part of your review as you identify a section that you may want to review more, where you've got a little less, comfort, a little less familiarity with, coming from a 151. You want to go back to those sections and you'll be able to pull them up specifically from the video. Now, what these topics are topics that you should have had in like a 151 or equivalent course coming into this course. I'm going to have questions on the first test based off of these 7 topics. And I've got references here to the chapters in the textbook that comes with the 152 class where these topics are discussed and where I have pulled questions and other materials for this presentation out of. If you'll reference the study guide for test 1, you'll see how I've broken down how many questions will be on each of these topics. There'll be at least one, some of them will have 2. There'll be a total of about 12 or 13 questions that'll come from this review material. So that's where you should focus. Now, in these 2 lectures, I'm going to go through each of these 7 topics. You may or may not need as much review on any one of the particular topics, depending on what you come into the course with. So you'll want to try to focus your time where you yourself and your background tells you where you're not as strong. And I'll have example problems that I'm going to pull from this text for each of them that'll be focused on how I'm going to test this material on the test. So starting here with net ionic equation. So we're looking at precipitation reactions. You should be familiar with those again from a 151 course. We look at the first equation. Now, they call this the molecular equation. I always find this a bit of a misnomer because there's no molecules in these. These are all ionic compounds. But the point is this is sort of the standard way that an equation, a balanced equation, is typically written. Again, balancing equations is one of our topics that we'll talk about a little bit. But here we're just looking at an equation, and we're looking at how it's broken down. Everything is grouped together. There's no separate ions going anywhere. We have this lead iodine that's falling out of solution in our ionic equation here. And then we have an ionic equation where we break everything down into ions. Again, what I'm looking for you to be able to do on a test is just be able to identify, how would we break these down into ions, and then identify, for example, spectator ions, those whose phase does not change. So you'll see here that the potassium is aqueous on both sides, the nitrate is aqueous on both sides. But the lead and the iodine do change phase. They're in an aqueous state on the left side. They become a solid. So that's what we're going to be looking for when we derive what the net ionic equation is. And that's what we'll see here on this slide. So we're cutting out the spectators. They've drawn a little line through it for us. And that may be like a question that you would see on a test or in some of the review, just identifying what the spectators are. So you may not even have to write all this out. This is diagrammed all out so you can see all the steps. But once you've identified what doesn't change phase, you'll be able to figure out what the spectators are maybe a little more quickly than it takes to write all this out. I won't have any questions that require you to write all this out elaborately. They'll generally be multiple choice questions where you'll have to pick the correct equation, the correct ionic equation, the correct net ionic equation for a specific set. But I want you to be able to see this one worked all the way out, just so you can see all the steps that they take here. As you can see, again, the net ionic equation is only where those things that end up with some phase change are left over. And again, typically that phase changes into a solid phase, but in theory it could also be to a liquid or a gas or something that removes them from that aqueous phase. So here's another example, a worked example, again from 7.2 in the text. And they give us a little breakdown strategy where they route out everything as ions to help identify what the spectators are. Again, that's not always necessary in every case, right? So again, we're looking for something that ends up changing phase. But if multiple things change phase, like in this example, the hydrogen and the zinc change phase, you see that in this net ionic equation, there are 2 species, and that's okay. The chloride ion is the thing that doesn't change phase. It's in an aqueous compound on both sides, so it's the spectator ion. I like this example because it shows that sometimes you can have something become gas or something change from a solid to aqueous, and that phase change is what you're looking for to identify. Not all textbooks will teach it that way, will kind of point you in that direction, but that actually does guide you to the best answer most quickly. And then here are some other examples. The answers to these are also in the textbook, but I pulled these out specifically because if you can do these, again, it doesn't ask you to write out all the full ionic equation for these. Just to write it down to the net ionic equation, if you can do these, identify the species that don't change phase for each of these three, you're solid enough that you could answer any of the questions I'm going to ask on the test. And if there are other problems around these in the same part in the textbook, in chapter 7, around 7.2, don't worry about them. Focus on these in particular. Do a little review of this. If you can do these and identify them like we talked about, then you're good to go on this topic. So oxidation reduction. So this is a topic not all 151 classes may go into in as much detail, so I have a little more on that here. So what we're looking for is oxidation as the loss of electrons by a substance, and reduction is a gain of electrons as a fundamental concept, right? So I talk about here as oxidation being loss, reduction being gain. Sometimes they'll talk about this as like the oil rig, the little mnemonic device. But I like the way the textbook depicts this as a direction, an arrow direction, right? Something being loss of electrons going right, and then gaining electrons going left here as the way they depict it. Another way, it's interesting that reduction is a gain of electrons, but we think of it as like a gain of negative charge. So it's a loss of the charge state. It becomes, as they say, less positive. It will gain electrons, and that will make it less positive. That's how things get the idea of reducing here. And generally, the term oxidation, loss of electrons, typically goes to oxygen when things burn or are corroded. So there's an association of that process with oxygen, just to help us grasp a little more why the naming is the way it is. It's kind of a historical holdover, but it does have some basis in the chemistry. So there are rules for assigning these oxidation numbers, right? Now, if you remember charge states and fundamental charge states for like a monatomic ion, if a monatomic ion has a charge state like the examples of sodium and calcium and aluminum in rule number 2, then their charge state is the same as their oxidation number. So we can think of oxidation numbers as like the grander scheme version of charge states. This allows us to assign these sort of fake charge states in molecules or other things that aren't really made up of ions. That's kind of the idea in the breakdown that we're doing here. So if something's in an elemental state, it doesn't have any kind of charge. It'll also have an oxidation number of 0. So that's our rule number 1. Our rule number 2, like we said, is if we have ions, we'll assign a charge to them based on the charge state they already have, their common charge state. In polyatomic ions, which are really molecules with charge or molecular compounds, what you'll do is break these down into components and assign some basic rules. So if these are atoms where you would have a common charge state as a monatomic ion, typically we can use that too in the breakdown, but it's not always entirely clear. Like they say, oxygen generally has an oxidation number of -2, just like it normally has a charge state of -2. Hydrogen is generally a +1 in molecular compounds, which includes polyatomic ions, which are molecules with charge. But it can also have a -1, just like it could have in a hydride as a monatomic ion. Similarly, in the examples here, nitrogen here is shown as having a -3, but it can also have a +3 in other types of compounds. So some variation is possible, but our general rule, and they'll talk about this in some of the other rules as we go forward, is that hydrogen is generally a +1 in some kind of molecule unless we're told otherwise, and oxygen is generally a -2 unless we're told otherwise by some context. And starting from that basis, we can then derive what other atoms might be in these polyatomic ions or molecules. So here they mention that in a little more detail, A, as hydrogen can be +1 or -1. Generally, hydrogen is -1 if it's in some kind of ionic compound or otherwise is with some sort of metal. They give that as the example number 2 with calcium and the example number 1 with sodium. But when it's with a nonmetal, it's in a molecule type thing like hydrogen chloride, then it's generally a +1. And we'll use that as a rule again to derive what other ones might be, right? Sulfur is an example of an element that can have multiple oxidation numbers, but in hydrogen sulfide here, we can see that it needs to be a -2 to go with the 2 hydrogens, which are typically going to be +1. Oxygen, again, generally is a -2, unless there's some other reason. Otherwise, the most common exception to that is when you have peroxides. These are typically where you have 2 oxygens in a row in the structure, or you have something that's written at O2 2-, where we almost would think of it as each oxygen having a -1 charge, and that's how we break it down here. The oxygens don't exist as a -1 charge. That's very, very unstable for them, so they'll come in a little grouping that's a 2-, that I can't divide. But in these instances with peroxide, that's the big exception where oxygen can be something other than -2. Here it's -1. Sometimes there are compounds with oxygen and fluorine that can break this rule too. Again, but it's mostly, generally, almost always it's going to be a -2. So we'll start with that unless we see some other strangeness going on. Halogens also typically have a oxidation number of -1. And we see that in this example where, well, the examples down below, actually, they're showing the exceptions, but it works up in the example we showed above with hydrogen, where it's a +1 and the chlorine's a -1. Typically, that's also their charge state as a monatomic ion. But we do get into some exceptions where we have things that are more electronegative than those particular halogens, like oxygen being more electronegative than chlorine, can make chlorine become positive to cancel out the oxygen. So there's sort of a set of priority, right? The thing that wants to become more negative is going to be the more electronegative thing. We remember electronegativity, again, is a 151 concept. The more electronegative thing is generally going to seek to be the negative one in whatever molecule system I'm going to set up. And that will force these halogens to choose a different charge state that will allow them to cancel out the negative charge of the oxygen, like here in the example. In Cl2O, the oxygen is the -2, and that takes priority over these halogens so that they can become a +1. That's another stable configuration for halogens being a +1 when they're with oxygen. And that's a big exception. Sometimes you'll also see things with halogens where, like if bromine is in the center and chlorines are around it, the bromine will want to be the more positive thing because it's the less electronegative halogen, and the chlorines will want to be more negative. So you can use a hierarchy of electronegativity to sort of determine where that needs to go. And also they try to put these rules generally in order, right? To follow these rules in this sort of order. So hydrogen, then oxygen, then the halogens following these particular rules. So you'll want to keep the first 2 rules in operation before you get to the third one, if that makes sense, the A, B, C in that sequence. And generally, so this is the other trick we'll use to determine missing things, right, or something where we're not sure. The sum of the oxidation numbers is 0 when it's neutral and equal to the net charge for something that's charged. They'll call them polyatomic ions here, but these are just going to be charged molecules. That's essentially the same thing. So sometimes you'll have a difficult atom where you're not sure, like sulfur. So in this example of hydrogen sulfate or sulfuric acid, if it's in water, we'll have a +1 for the hydrogens and a -1 for the oxygens, and we use that to derive what the sulfur is as a +6. Now, some periodic tables will list all the common charge states. You can look at those, but not all of those are perfect. And when you have problems like this where you're asked for potential missing species like this is a pretty typical problem. You'll want to use the rules before. Usually you'll use hydrogen and oxygen first to then derive what that missing other species is. Again, in this perchlorate anion, they do the same thing. There are these 4 oxygens. They're all -2, so that gives us like a -8. But then the overall charge is -1, so we'll need a +7 to make that -8. The 4 times -2, plus the +7 to get the -1 for the overall charge. And it actually turns out +7 is another stable state. Oftentimes these additional charge states are a sort of backward way of reaching a noble gas. Like for sulfur, a +6 is an emptying out. Instead of gaining 2 more to reach 8, it'll lose 6 to go backward. Similarly, for halogens, a +7 tends to be pretty stable for them because they'll lose all 7 of their electrons to go back to their last noble gas instead of gaining 1 more to go forward. We'll see this can also happen with things like nitrogen and phosphorus, where they'll go backward instead of forward. That's another way we can predict, is this number we got from this process something realistic for that atom? And being in molecules, you're allowed to have these really high charge states like +6 and +7 that would just be not possible if they were monatomic. They wouldn't be able to withstand that much positive or even negative charge on a small atom like this. So that's something else to keep in mind. I got another example down here of ammonium, right? So it's got an overall positive charge. We got 4 hydrogens. We're going to say that those are +1. So that'll tell us that the nitrogen must be -3. And that's a common charge state. That's typically a charge state. For nitride is a -3. So there it all works out very well. But we can, what the examples are showing us is a neutral, negative, and +1 example. So then we've got some quick examples here. So they say assign oxidation numbers to the atoms in the substances, right? So the first example looks like some kind of ionic compound because you got cadmium, that's a metal, with sulfur. So even if we didn't know what cadmium was, we could check what sulfur typically is in an ionic compound. It's typically a -2, just like oxygen. It's in the same family as oxygen, and we would see that on the periodic table here. So typically oxygen gains 2 more electrons to reach its nearest noble gas. Sulfur can also gain 2 electrons to reach its noble gas since it's in the same family. So that gives us a prediction for what the charge of cadmium is. And again, if you check the table that has oxidation numbers, you would find that +2 is a valid charge state for cadmium. But you wouldn't need to know that in order to answer the question. You'd really just need to know about sulfur. Looking at B, we know that aluminum is generally a +3. That's one of our common ions we would run into in a 151 class. So in this example, hydrogen would have to be -1. And that works out because hydrogen can be +1 or -1. And since it's with a metal, it's often -1 instead of +1, as it is in most molecular compounds. In C, we're going to say the oxygen is -2. There's 3 of them, so we're going to get an overall -6. And then we'll have to cancel out 4 of that -6 to get to -2. So we can see with the sulfur, that should be a +2. So we can get that overall net charge. That's the kind of reasoning that we're using. We can almost set up a little equation like the textbook does to say that we've got 2 +2s, which will be the sulfur, 3 -2s, so that we can get the overall -2 charge we're looking for. We want to kind of solve this algebraically and think about it. Often elements like sulfur can have a variety of different oxidation numbers, so we'll want to check that. Again, often it's a +2 or a -2, but sometimes we'll also see +6. The complete emptying out of the table. And we'll look in D here. Now, sodium only has a +1 as a possibility, so we can almost just sort of ignore that in D and say that dichromate is a -2 overall, so that it can cancel out those sodiums. We have 7 of these oxygens, so we'll have to multiply that by -2 and get like a -14, and then we can look at the chromium. Now, we want to get that to be -2, and we'll need to have the chromiums generally both be the same. Generally, in a compound, if there are multiple of the same element, they'll all have the same oxidation number. There are some exceptions to that in more complex situations, but for all the ones we'll run into here, that'll be true. So if we assign the chromium a +6, which is a valid state for chromium, it's very high, but it's a valid charge state for chromium, we can multiply that by 2 and get +12, plus the -14, which will give us -2, plus the 2 sodiums, which will cancel all that out. Again, it seems kind of elaborate, but if you're writing down like they're doing in D, they're making a note of what each of the charges is, and then kind of what the overall needs to be with it being neutral, you'll be able to see that ultimately you're going to be looking for that difference piece that you need and then dividing it by however many there are, just like we would divide a potential missing charge in C by 2 because there's 2 sulfurs. We can divide that potential 12 missing charge by 2 because there's 2 chromiums. And then there's a couple more examples in 7.3 that have the answers in the text as well for you to review if this is something else you want to go through. But they'll have similar questions to this on an exam where I'll give you an example compound and ask you to assign something, or I'll give you an equation and ask you what happened to the charge state of some particular element. And we'll look at that in a few other examples. This was just assigning states. Next, we're going to look at identifying who's oxidized and who's reduced in an equation. Okay, so if we have a balanced equation that is a true redox reaction, then there will always be something oxidized and something reduced. So something that's oxidized is going to lose its electrons and something reduced is going to gain those. And there'll be some kind of electrical transfer in the course of this reaction where, since charge needs to be balanced, the number of elements needs to be balanced, then the number of electrons transferred must also be identified. So we have 4 irons here, and these 4 irons are also on the right side, and they're undergoing a change from 0 to the +3 state that they have in the iron 3 oxide on the right, and the oxygen is going from the oxygen gas to the 2- state that it has on the other side. So what we're going to do then is identify these as something that undergoes an oxidation and something that undergoes a reduction. So we'll say that the iron is oxidized and the oxygen is reduced because it became more negative, and the iron is oxidized, it became more positive. And again, they show that, again, here in another example where we can identify who is oxidized and who's reduced. In this example, the iron is reduced. It goes from +3 to 0, and the carbon is oxidized. It goes from 0 to +4. So then we'll need to learn the agent terminology, as they'll call it. Sometimes they'll ask you to identify the reducing agent or the oxidizing agent. Note that these are reversed. The reducing agent is the thing that is oxidized, or the species. Typically, they'll want you to identify the entire species in the balanced reaction when they do that. And the oxidizing agent, of course, is the one that undergoes the reduction. And again, the species is a particular thing in the reaction they'll want you to identify. So when they call it the oxidizing agent, they say it causes the oxidation, but it itself gets reduced. And the reducing agent undergoes an oxidation, so it itself, even though it causes the reduction. So we'll see that these are kind of backward. But that's just something else we want to note. So there'll be example questions where you'll need to identify the oxidizing and reducing agent. And in these examples, they show you have to identify what happens to each one. So the calcium in A loses electrons so that it can become positive. So it is oxidized, so it is the reducing agent. And then conversely, the hydrogen gains electrons, so it is reduced, and thus it becomes the oxidizing agent. I like the way that the text labels these in the strategy for A in particular, because it not only points out what happens to the species, but then it also gives you the agent notation, and you can see how they're backward, quote unquote, because they're doing the thing, not the thing that happens to them. And then they look at another example here very quickly with the same basic idea. We identify who's oxidized and who's reduced, and then we identify the agent. So the thing that gets oxidized becomes the reducing agent, the Fe2+, and the chlorine becomes the oxidizing agent because it itself is reduced. It goes from 0 to -1. If something, another way to think about it is a thing that's playing the role of oxygen, that's taking electrons away from something else, is the oxidizing agent because it's the thing that gets reduced. And then again, I have some other example questions in 715 if you want to review this further. So quickly here we'll look at electron configuration as well. So this is where we'll be writing out the like the 1s, 2s, 3s, 2p type of configuration we learned in a 151 class. We'll quickly look at the rules here. So generally lower energy orbitals are going to fill before higher ones. An orbital can only hold 2 electrons. If 2 or more degenerate orbitals are available, one goes in until they're all half full. But what I really want to point you to is the periodic table, right? If you can identify which block an element falls into, you can figure out where the highest energy position is going to be. And the text has a nice little workout where if you start from hydrogen and you work your way through the periodic table, you can build a configuration pretty broadly. And this might be a topic that confused you in a 151 class. It was never really pointed out exactly how to do these kinds of questions. So I want to show you these diagrams because I think these are, the ones I ask are generally pretty straightforward, and I just want you to be able to start with sort of a good foundation of using the periodic table to solve these, right, and using the block diagrams to help out particularly. So they talk here about some anomalous configurations, right? We know that chromium, if you have a 4d, you gain an extra electron. If you have a d9, then you gain an extra electron. So 4s go to 5 and 9s go to 10. Again, not a major topic, but just something to to make note of. But I'm going to look here at an example first, right? So they say they want the ground state electron configuration. That's just the standard one. They tell me Z is 33. So there's 33 protons. That means there's 33 electrons, right? So we can walk the table. What we can do is start from hydrogen and walk the table until we reach the arsenic at 33. We know we're going to end in 4p on this periodic table, which helps us out here. So if we start with hydrogen, we can go 1s, 1, 1s2, 2s1, 2s2, and then the 6 2p's, then the 2 3s's, then the 3p's, then the 4s's, and the 3d's, and then we end with the 4p3, and there's 10 d's. So these just go in order as you walk down the periodic table. They say the order of filling is the same as the order the elements are in the periodic table. So we can just follow the periodic table to get back to our configuration. So this is where we got the 4p3. It was the third element, which we saw. The 3d10 was right before it. The 4s, the 3p6. We walked through each of these in sequence, and we can start from the last noble gas that came right before it, and that's the noble gas condensed configuration. This is as complex a problem as I would ask on an exam, and I just want to make sure that if this is a topic that you never really fully understood, please take some time to go through this periodic table that I've pulled out of the textbook for the slides, because if you learn how to walk the table like I just did in the example, you'll be able to do any questions like this on the exam. I want you to learn how to use the periodic table to do these kinds of questions. Sometimes they'll teach students to draw these little pyramids or do silly things. I would just say walk the table, and learn the different blocks. If you've got a periodic table you like to use, you might want to color your blocks to match this all up. If that's something like you did in a 151 class, that may help you. Doesn't really matter what the colors are. There's no particular color. It's just a way to show you where the blocks are so that you always know where things end, and that'll help you get to the answers to these kinds of questions. So again, they say one way to do this problem is to identify it and decide which atom has it. You can count the electrons, which is really what we're doing. We're just counting the electrons. And they give us some other examples here of titanium, zinc, tin, lead. I'm not going to ask for anything that's really heavy that have more exceptions. The only two exceptions you should really know are the D4 and D9 exceptions for the families of copper, silver, gold, and chromium, molybdenum, tungsten over on the D4 side. I'm not going to ask about any of the heavy elements down here. I'm not going to ask about F stuff. I'm going to keep it very simple and straightforward. So that's why I use these examples here, because none of them really need to get wacky and weird. This is as complex as you'll need to understand. Okay, so we'll also take a quick look at balancing equations. Again, this is a pretty simple topic from a 151 standpoint, something you probably learned pretty early on in the class, but if you never quite had a good system to it, I like the way that the book breaks this down. So you start with the unbalanced equation. You'll typically want to balance everything other than oxygen and hydrogen first. So like in this example, we can tell that there's a carbon, one carbon on both sides, one carbon atom on both sides already. So then we'll have to start by trying to balance the oxygen or the hydrogen. You kind of pick one first. You could put the two basically on the water, H2O, or put the two on the oxygen first. It's kind of up to you. But whenever you run into something that's like odd on one side or even on the other, like for example on the right side here you have 3 oxygens and only 2 oxygens on the left, you'll need to double the oxygens in order to make that work. That's kind of what I'll call the even-odd note. That's something that if you had never really learned how to do, it might have tripped you up on some of these more complex balancing situations. And this is a real simple one, but it still has that going on. So you have 3 oxygens and you have 2. So we're going to need to make the odd thing even. There's no real way to make an even thing odd. So we'll want to somehow make this odd thing even here by putting a 2 in front. It's really the major notes here. And then here's another example of a propane. Now, there are a lot of websites out there you can find that can also help you do these balancing, so you'll find a way to check your answers with ones that you're doing. Like you don't use them on a test, but you can use them to, if this is an area where you're kind of weak, take those problems that can always confused you and put them in there and make sure that you've kind of figured out where you need to go, right? So again, I'm looking at this one. I'm going to start by balancing the carbon because I'm going to start with something other than hydrogen and oxygen first. Okay, so we did that first step. Then they picked hydrogen to do next. You could have picked the oxygen next. It's not always clear which one. So they balanced the hydrogen next by putting the 4 over here. And then in the next step, we put a 5 over here to balance all these oxygens to make that work. Notice we put this on the left side because the right side already had an even number of oxygens. We were already up to 3 times 2, 6, plus 4, 10. So the 5 over here fixes that. And then if you're not in your smallest whole number value, you can reduce. But if you follow the process, you generally will not end up at a higher point. So like I say, start with the elements that are not hydrogen and oxygen first. We start with carbon first, put the 3 here to fix the 3 carbons. And you can also, what I'll also sometimes recommend students do is keep track to write down how many things are on each side, make a little table, like a little scoreboard. And then whenever you add a number, you update your little scoreboard. This can help you if you're struggling with this. Again, a lot of students kind of find their own way to do these because there's a little bit of common sense that's involved in the balancing. You have to kind of do the problems to see it. But the basic approach, do everything other than hydrogen and oxygen first, and then do hydrogen and oxygen, I think is the most important. And then when you have something that's even on one side and odd on the other, you got to somehow find a way to make the odd thing even. If you keep those 2 things in mind, you can generally balance any of these without any real difficulty. So you can see that basic idea here. And then I've got some other examples that I pulled here if this is an area you're struggling with. Again, some of these are even more complicated than anything I would put on a test, but they're just really simple, straightforward balancing. And I especially like C because it gives you multiple things other than hydrogen and oxygen to do. That might be a good one to start with. Some of these hydrogen and oxygen ones can get a little bit complicated. But I think B and C are probably the best ones out of these. In fact, yeah, I'd probably say those 2 are the best ones to reach to if you're looking for ones for more practice. Okay, and that is the end for this part of the presentation, but I'll be continuing in the second part. So see you then. Take care. Bye-bye.